You type a handful of words, and seconds later a picture appears that has never existed before. It feels like magic, but it isn't. Underneath is a chain of very specific steps, each one doing a small, understandable job. Today we're going to walk through that entire chain, from the letters you type to the pixels you see. Let's use one prompt as our companion for the whole journey. We'll ask for a red fox sitting in a snowy forest. Keep that sentence in mind because we're going to follow it through every stage of the machine. By the end you'll know exactly what happens to each of those words. Here is the roadmap for our trip. The words get chopped into tokens, the tokens become vectors, a text encoder blends them into a single meaning, and then a denoiser slowly sculpts an image out of pure noise while constantly consulting that meaning. Finally, a decoder blows the result up into a full picture. 5 stops, 1 sentence. First stop, tokenizing. Computers don't read words the way we do. Before anything else, the sentence has to be broken into pieces the model recognizes. Those pieces are called tokens, and they come from a fixed dictionary the model learned once and never changes. A token is often a whole word, but not always. Common words like fox and snow get their own single token. Rarer or longer words get split into smaller fragments, so unusual text still fits in the dictionary. This way, a fixed vocabulary can represent almost anything you type. Each token has an ID number, its address in the dictionary. So our sentence turns into a short list of integers. That's all the model sees at this point. Not letters, not meaning, just a row of numbers pointing into a lookup table. The model also quietly adds a couple of special tokens, one marking the start and one marking the end. And it pads the list to a fixed length so every prompt, short or long, has the same shape. Machines love predictable shapes. It lets them process everything in neat, uniform batches. Second stop, embedding. A token ID is just an address, and an address carries no meaning. To give the model something to reason about, each ID is swapped for a vector, a long list of numbers. Think of it as looking up each token in a giant table where every row is a coordinate in a vast space of meaning. Why a vector and not a single number? Because meaning has many dimensions. One direction in this space might track how animal-like something is, another how cold, another how bright. A word is a point positioned along hundreds of these axes at once. No single axis is labeled, but together they pin down a shade of meaning. In this space, similar things sit close together. Fox lands near wolf and dog, snow lands near ice and winter, and red lands near crimson and scarlet. The embedding table was tuned during training precisely so that geometric closeness matches real-world similarity. Distance becomes a stand-in for relatedness. But there's a catch. Right now, each token is embedded on its own, in isolation. The vector for fox is the same whether the sentence says a red fox or a fox terrier. On its own, embedding doesn't yet understand that these words belong to one sentence and modify each other. That's the next stage's job. Third stop, the text encoder. This is where the words stop being a list of separate pieces and start becoming a single coherent idea. The encoder reads all the tokens together and lets them talk to one another, so each word's representation gets colored by everything around it. The mechanism that lets words talk is called attention. Every token gets to look at every other token and decide which ones matter for its own meaning. The word snowy leans on forest. The word red leans on fox. Attention is just a weighted glance. How much should I listen to each of my neighbors? After this mixing, the vector for fox is no longer generic. It has absorbed that it's red, that it's sitting, that it's surrounded by snow. Every token has been updated to reflect its context. The isolated points from before have become context-aware. Stack this attention step many times, and the encoder builds a rich, layered understanding of the whole phrase. The output is a set of conditioning vectors, one polished vector per token, together forming a compact summary of what you asked for. This bundle is the sentence's meaning, translated into the model's native language of numbers. Hold on to this conditioning bundle because it's the star of the second half of our journey. It won't draw the image itself. Instead, it will act like a client giving directions to an artist, whispering the same instructions over and over until the picture matches. Let's go meet that artist. To understand the artist, we first need to talk about noise. Take any photograph and start sprinkling random static onto it, a little at a time. Keep going, and eventually the picture dissolves completely into pure random speckle, with no trace of the original left. This gradual destruction is the key idea behind diffusion. During training, the model watched this happen to millions of images. It saw clean pictures turn to noise step by step, and it was asked one question again and again: given this noisy image, what noise was just added? Learn to answer that, and you've learned something powerful. Here's the beautiful twist. If the model can spot and remove the noise that was added, we can run the whole process backwards. Start from pure random static and repeatedly ask the model to remove a little noise, and step by step a real image emerges from the chaos. Generating a picture is just denoising, over and over. But denoising pure static could give you any image at all. What makes it become a red fox and not a beach or a city? This is exactly where our conditioning bundle comes back in. At every denoising step, the model peeks at those instructions and steers its cleanup toward matching them. There's one more clever trick that makes all of this practical. Working directly on full-resolution images would be enormously expensive because a big picture is millions of pixels, so the model doesn't work in pixel space at all. It works in a compressed, shrunken world called latent space. Picture the difference. A finished image might be 500 pixels on each side, 500,000 little color values. The latent version is a tiny grid, maybe 64 by 64, holding a compressed essence of the scene. Every step of denoising happens on this small grid, which is why the whole thing runs fast enough to be useful. A latent isn't a blurry thumbnail, though. Each cell in that little grid doesn't store a color. It stores an abstract summary of a whole patch of the eventual image, things like texture, shape, and material. It's a coded description, not a shrunken photo. We'll decode it back to pixels at the very end. So let's restart the generation properly, in latent space. We begin with a tiny grid filled entirely with random numbers. This is our block of marble, formless and meaningless. Everything that follows is the artist chipping away at it, guided by your words. The artist doing the chipping has a name, the U-Net. It's the neural network that takes the current noisy latent and predicts how to clean it up a little. It's called a U-Net because of its shape, and that shape is worth a quick look because it explains how the model sees both the big picture and the fine details. On the way down the U, the network compresses the latent even further, zooming out to grasp the overall composition. Where the fox sits, where the sky is, the broad layout. On the way back up, it zooms in again, restoring detail like fur texture and individual snowflakes. Down for the gist, up for the specifics. Now for the moment we've been building toward, how do the words actually reach into this denoising process? The answer is a mechanism called cross-attention, and it's the bridge between your sentence and the image. This is the heart of the whole system, so let's slow right down. Earlier, attention let words look at other words. Cross-attention is the same idea, but across two different worlds. Here, each little region of the image gets to look at each word of your prompt. A patch that's forming into fur can ask the whole sentence, which of these words is about me? So the region destined to be the fox reaches across and pulls hard on the words red and fox, while the surrounding region pulls on snowy and forest. Each part of the image latches onto the words most relevant to it. The prompt isn't applied uniformly, it's distributed word by word to the places that need it. And this doesn't happen just once. Cross-attention sits inside many layers of the U-Net, so the text gets consulted at multiple scales at the same time. At coarse levels it shapes the overall composition. At fine levels it steers texture and color. Your words are woven in everywhere, top to bottom. Let's put the loop in motion. The U-Net looks at the current noisy latent and the prompt, and predicts the noise to subtract. We remove a slice of that noise, and the latent gets a tiny bit cleaner and a tiny bit more fox-like. Then we hand the result straight back in for another round. This repeats, typically for a few dozen steps. Watch the latent across those steps and you'll see structure swim up out of the randomness. First vague blobs of light and dark, then a rough silhouette, then the unmistakable shape of an animal against a pale background. order condensing out of chaos. It helps to think of each denoising step as answering a question. Of all the images this could still become, which ones both look realistic and match the prompt? Every step narrows the possibilities, ruling out the pictures that don't fit. The noise is the space of everything. The words carve out the fox. This is also why the same prompt gives different pictures each time. The starting noise is random, so each run begins from a different block of marble. The words constrain what the image must contain, but they leave enormous freedom in the exact pose, lighting, and background. Randomness plus guidance equals variety. There's a knob worth mentioning that controls how strictly the model obeys your words. Turn it up, and the model clings tightly to the prompt, sometimes at the cost of looking natural. Turn it down, and it drifts freely, prettier but less faithful. This dial is often called guidance strength, and it trades obedience against realism. Under the hood, that dial works by a small trick. The model actually makes two predictions each step, one with your prompt, and one imagining no prompt at all. It then pushes away from the promptless version and toward the prompted one. The bigger the push, the stronger the guidance. It's a nudge in the direction your words point. After all the denoising steps finish, we have a clean latent. But remember, this is still that tiny 64 by 64 grid of abstract codes. It is not yet a picture you could hang on a wall. It's a finished blueprint that still needs to be built out into real pixels. Fifth and final stop, the decoder. This is one half of a component called the variational autoencoder, or VAE. Its whole job is translation between the two worlds we've been discussing, the compact latent world and the full pixel world. We've been living in latent space. The decoder brings us home to pixels. To appreciate the decoder, meet its twin, the encoder. Back during training, the encoder did the opposite job. It took real full-size images and squeezed them down into compact latents. It learned to throw away redundant pixels while keeping the essential meaning. The decoder learned to reverse that squeeze faithfully. So the decoder takes our little grid of abstract codes and expands it, cell by cell, into a large field of actual colored pixels. Each latent cell, remember, described the texture and shape of a whole patch. The decoder caches those descriptions in, painting the real fur, the real snow, the real light, at full resolution. And there it is. Out of the decoder comes the finished image, a red fox, sitting in a snowy forest, exactly as requested, yet an image that has never existed until this moment. Random noise went in, your words steered the sculpting, and a coherent picture came out the other side. Let's rewind and see the whole chain in one breath. Your sentence was chopped into tokens. The tokens became vectors. The text encoder blended them into a bundle of meaning. That bundle guided a U-Net as it denoised a tiny latent from static into structure, and a decoder blew that latent up into pixels. Notice how the two big ideas fit together. Latent space is what makes it fast. All the hard work happens on a small grid instead of millions of pixels. Cross-attention is what makes it obedient. Your words are pulled into the process at every step and every scale. Speed from compression, control from attention. It's worth pausing on how little of this is hand-coded. Nobody wrote rules for what a fox looks like or how snow catches light. Every one of these stages, the embeddings, the encoder, the U-Net, the decoder, learned its job purely by watching millions of image and caption pairs. The structure is designed, the knowledge is learned. This also demystifies the failures. When a model muddles a prompt or garbles fine details, it's usually the cross-attention struggling to route the right words to the right regions, or the latent being too coarse to hold the detail. The magic has seams, and now you know where to look for them. So the next time a picture materializes from a sentence, you'll see past the magic to the machinery. Words become numbers, numbers become meaning, meaning steers a slow climb out of noise, and a decoder unpacks the result into something you can finally see. That's text to image, end to end. If this made it click, subscribe for more visual math.